Welcome back, everybody. So we are in our second set of notes in this unit, or this target, that's really talking about functions and transformations. Now, in the last notes, if you've watched that, we were classifying all the different functions. And I like to think of that a little bit kind of like classifying animals. You have all these families and genus and species, and so there are certain traits that group them together. Mathematicians do the same thing, but we do them with functions. And so now we're going to start to really learn some of the smaller details about how we can transform them. We have these families, but out of those families we can have many different types of graphs. And we'll see how that works today using numbers. Go ahead and look at our B notes here. If you're looking at this picture and you notice that it's a V shape, that should ring a bell in your head. Those types of graphs are called absolute value graphs. Now, if you read the directions, you already knew that. But we're going to call this absolute value f of x. So a lot of times I reference that as just the name. So maybe this is Fred or Frank. And so Frank is this absolute value graph, and if you're looking, you should know that it's the parent absolute value graph. It's centered at the origin, and its pattern is very simple. The slope of each arm is just 1 over 1 over 1 for its rise and run. Now with this, we're going to go ahead and look at the first two questions where I take Frank and I start introducing numbers just to see what it does. It's a bit like an experiment. And so in number 1, it says graph f of x plus 1. What does that plus 1 at the very end do to Frank? Now if you're coming up with a hypothesis, we can test that hypothesis. Go ahead and take a moment and just write down your first thought about what plus 1 will do to the graph. If you look at number 2, that is very similar. It says f of x, but minus 2 is at the end. So we have one version where we add and one version where we subtract. Take a second, again, to write down your hypothesis for what subtracting would do if it's included at the end of the equation. We're going to go ahead and we're going to move over to Desmos to visually see what happens. So in Desmos, I have Frank already set up. And we're going to take that parent graph and we're going to add in some of those transformations. So we'll do plus 1, and you can see the graph is hovering above the original. And so if you wrote moves up 1 in your little hypothesis, you got that correct. You have great intuition about what some of these numbers are going to do. Now, thinking of the second problem where we have minus 6, that is going to move the graph down 6. And so we'll type that in and we'll see exactly what that looks like. Now it's really cool because Desmos allows us to use sliders and we can shift our graph almost like a movie. So I'm going to change it and allow it to be fluid, moving up and down, and you can see depending on if it's plus or if it's minus, you might be shifting it vertically up or shifting it vertically down. So that's the first type of transformations. If you add or subtract numbers at the end, you are moving the graph up or down, and that should make sense if you understand the symbol notation for functions. Remember yesterday we talked about f parenthesis x parenthesis f of x. The most basic way to understand that is that it's a fancy way to say y. And literally what these problems are saying is you take the y and you add 1 to it. So all the y values will be 1 greater than what they were. So the heights will be 1 greater. Or you take the y values and you subtract 6 from them, which takes the whole graph and it moves it down. So when we discussed what functions are, that was all very important stuff. And now you can see how they start to connect together with the transformations and the movements. Let's look at number 3. 3 and 4 are similar, but just like an experiment, we're testing a different position now. So before, while we had the number at the end, what would happen here if we have numbers inside? So you'll notice it says f parenthesis, and then inside those parentheses is x plus 3. Number 4, very similar setup, except that it's x minus 2 in parentheses. Take a moment, go ahead and make a hypothesis for what you think the plus 3 and the minus 2 will do to the graph. Will it move it? Will it stretch it? We already know one of the options is moved up and down, so this probably will do something different. Going back to Desmos, we're going to clear out what we had and we're going to start with the first problem here. Plus 3 inside, if you're looking, does something weird. Most people are going to say that plus 3 would move the graph right 3. But if you're looking at what Desmos does, it's actually doing the backwards version of that. It's moving it left. And so a lot of times I'll have students who are working ahead and they have to erase all the work and the entire graph that they wrote down. But did we break math? Or what's going on here? Let's go ahead and let's type in the x minus 2. If we look at what's happening there, that is actually moving right 2. And so the action that's going on here seems to be counterintuitive. We're shifting this graph right and left horizontally, but we're doing it in a backwards manner. Now, a few things on this. If you really understand kind of the setup of how functions work, what are we impacting here with the plus 3 and the minus 2? Well, it's right next to x, so we're impacting the x values. The x values go left and right, so you can logically deduce that this is a movement in those directions, but why is it backwards? One thing that we don't do a good job at, just as people, is seeing things from different perspectives sometimes. What we like to do as students is put ourselves as the function. That is us. And so we like to think that we are moving in a certain direction. But what's really true here is that we are taking the coordinate plane, the background, if you will, and we are moving that coordinate plane. So if it says x plus 3, it's moving that coordinate plane 3 to the right, which leaves the function behind. So it appears like it's 3 to the left. Same idea if we were going ahead and putting x minus 2 in there. It takes the coordinate plane and it moves it 2 to the left, making the function appear as if it was left 2 spaces to the right. And so this is why that action appears backwards. That's something not a lot of people know coming into Algebra 2. And it takes some learning and it takes some practice to override that initial assumption. To summarize the first page, if we add or subtract numbers at the end of an equation, we're moving our graph vertically. We're moving the function vertically. If we add or subtract numbers inside with the x, we're translating our graph horizontally, left and right, and it's backwards. So let's move on to the back of these notes. These are quick notes. We see some of the last types of transformations here in 5 and then 6. So number 5 says 2 times f of x, 2 times Frank. Now if you think about that and make a hypothesis real quick, what is going to happen to the graph? My first thought is, what if I took 2 times myself? What if I am Frank? And so thinking about my height, I'm about 6 feet tall. 2 times that height would make me 12 feet tall. And just like you saw in the other video, stretching things, we are stretching them vertically. So if you wrote down a vertical stretch, you're absolutely correct. Let's go on Desmos and let's see how that works. So you can see, it appears to be getting squished, but you have to override that thought and think about stretching it out. Proportionally, it's just going to look thinner. It's not actually any thinner. It's vertically taller. Now, one thing that's an important point is that when you stretch something away from an axis, like if I were stretching myself, my feet will stay on the ground. Okay, they don't move, but my head gets amplified to be more extreme. And so my head is 12 feet in the air, 6 times 2 is 12, but my feet are still on that original axis. So you're kind of expanding away from that axis. Points that rest there don't change. Looking at number 6, we have a negative in front of f of x. That negative takes the whole graph and it inverts it. Now we are only going to be flipping or reflecting things vertically. And so if you were working ahead and you wrote down your hypothesis of reflecting or flipping, you are spot on. Good for you. So visually we can see that Frank is that V shape where all these positive y values are going up and it's making that particular pattern. When we take those y values and we reflect them and negate them, they're going to be hanging upside down. And so every height goes from being positive to being negative. One thing that the notes don't mention is what happens when you get smaller numbers being multiplied. And just like how numbers that are bigger stretch it out, numbers that are smaller actually crush it down. They compress the graph. And so when you actually hit the play button and see the motion of this front number, this front position, you can see that it gets stretched out and then it gets compressed back down, and then at some point it flips because those values in front are negative. Now mathematicians like to call these different positions of the front, the middle, and the end. They give them letters, and I almost have said the letter a few times, but that's something we'll learn in the next series of notes. So down below we have 4 different problems that we're going to practice with. They're different graphs, and they have different names, and we're going to apply transformations to those graphs. Number 7, h of x. If you're really thinking about what that is and what shape you're dealing with, that's a quadratic. So maybe we'll name this quadratic Henry. And so Henry has minus 3 at the end of its equation. Now if you're going back and you're thinking through the different places and what they do, minus 3 at the end takes the y values and moves them down. So at every y value, you're going to shift down 3 units, no matter where you're at. The end result looks like this. Question number 8, it's called f of x, so maybe it's Francine. And the type of function that Francine would be is a cube root. If you're having trouble identifying things, you can always go back and reference the notes from earlier. So Francine has x minus 2, where that is inside of the parentheses. Now that's horizontally moving it, but remember it's backwards from what you want to say right away. And so minus 2 is moving us right 2. That is a translation horizontally right 2 units. So we take all of those points and we shift them over right 2. And you could even say that there are points in between the nice points that we typically give you. That entire curve is made up of trillions and an infinite number of points. Kind of like pixels on your phone make pictures or images when you lump them all together closer and closer. Moving on to that third question, this is W, and inside you have x plus 4. So maybe this is Wayne, and the x plus 4 inside that quantity says left 4. Now if you're looking at Wayne and the shape that he is, he's a square root graph. So we take all of those points on that square root and shift them left 4. That's it. Once you get better at identifying them and once you get to know the patterns that go with each graph, this is really quick. It can be something fun and fast that you're asked to do. The very last thing on these notes is taking p of x, and there's a negative in front, so that would be reflecting p of x. You'll notice with the original picture though that p of x is already upside down. So it's not that we don't do anything to it, it's that we take all of those y values, that's what the p of x really stands for, and we negate the fact that they're negative, which makes them positive. So those heights get flipped up above, and that central vertex point, the tip of the V, since it has a height of 0, a y value of 0, it stays exactly where it was. Now if this had crossed over the x-axis, if there was some above and some below, the part that would have been above would go below, and the part that was already below would go above. And so you're rotating and flipping around that axis. If you're going to identify this, because I forgot to mention that at the beginning, that's an absolute value graph. It's a V-shape. So hopefully you're feeling more comfortable identifying the function that you're dealing with, just like it's easy to identify animals, and hopefully you're getting a better appreciation for what front numbers, middle numbers, and end numbers can do to the image of a function. Stay tuned for the next notes where we start to get more practice at this and introduce a couple of levels and we start combining them together to form more complicated questions. Great job, guys. Take care, and we'll see you in the next video.